Hello everyone. This is the third video in a playlist of structural isomerism. In this video, if you see the list of contents, I'm going to discuss the definition of isomers, isomerism, classification of isomers, means different types of isomers I'm going to discuss. Most importantly, the different types of structural isomers, the basic definition with example, and finally, what are the different hints we can use to identify the relation between the given structural isomers. And this video is definitely helpful for the students who are learning isomerism first time. This is the basic video. I'm going to teach the complete structural isomerism from the basics. First, let us take the exact meaning of isomers. Here, I'm taking two organic compounds. One is CH3CH2OH and another one is CH3OCH3. These are the two different organic compounds, but they have same molecular formula. So two carbons, six hydrogens, one oxygen. Here also two carbons, six hydrogens, one oxygen. So compound 1 and compound 2 have same molecular formula, but they have different properties, physical properties, chemical properties. Here these two molecules, that is 1 and 2, are said to be isomers. Iso means same, mer means a molecule. But most importantly, now if you see the exact definition of isomers, the phenomena of existence of two or more compounds, this is compound 1, this is compound 2, but they have same molecular formula. Molecular formula is the same, but they have different properties. They have same molecular formula but have different properties, maybe physical properties or chemical properties, and this phenomena is called isomerism, and these two molecules are called isomers. Not only this, let us take one more example to understand the definition of isomers. For example, I am taking CH3CH2COOH. Whenever you see one organic compound, immediately try to give its systematic IUPAC name, so that it will give you complete perfection on IUPAC nomenclature. This is a propanoic acid. I am taking a different organic compound that is having the structure like this. But if you see, both of them have same molecular formula: 3 carbons, 6 hydrogens, and 2 oxygens. Even this is also having the same molecular formula. So these two organic compounds have same molecular formula, but the physical properties and chemical properties of these compounds are different. Therefore, these two are said to be isomers. So this is the exact definition of isomerism: the phenomena of existence of two or more compounds having same molecular formula but different properties. This phenomena is known as isomerism, and the compounds are called isomers. Now let us take classification of isomerism, the different types of isomers we are going to discuss. Basically, isomerism is classified into two types. One is structural isomerism, another one is stereoisomerism. But in this video, I'm going to cover only structural isomerism. So, in case of structural isomerism, this is further classified into six different types: chain isomerism, positional isomerism, ring chain isomerism, functional group isomerism, metamerism, and tautomerism. So, even though we have six different types of structural isomerism, at this point of time, we cannot understand tautomerism, tautomers, Tautomerism and tautomers can be discussed only after completion of the general organic chemistry. So we are going to cover 5 types of structural isomers in this lecture: chain isomers, positional isomers, ring chain isomers, functional isomers, and metamers. Structural isomerism is also known as constitutional isomerism. So first let us take the exact definition of a structural isomers. The compounds having same molecular formula but different structures or different connectivities. So the compounds having same molecular formula but different structures or connectivities are classified as structural isomers. That means the two compounds which have same molecular formula but different structures are said to be structural isomers. So what is the exact meaning of a structure difference? How to understand this? The different types of structural isomers. Here I'm just providing the hint. Whenever you are trying to identify the relation between the two isomers, whether they are structural isomers or not, if they are structural isomers, which type of structural isomers they are not, if you want to identify, you have to check 5 important things. So the hint I am providing is, in case of a structure connectivity, if you want to identify, you just check length of carbon chain in the given compounds, position of a functional group or position of substituent, or both you can compare in the two compounds. What type of a functional group they have, you need to check. And the alkyl groups are attached to the functional group, whether they have same alkyl groups in both the compounds or different alkyl groups, you check. And even you have to check carbon framework, open chain compounds and closed chain compounds. So if you can understand these 5 points, it will be very easy to understand the 5 types of structural isomers. Now let us get into the definitions of 5 types of structural isomers. The first one is chain isomerism. If you see the definition of chain isomerism, the structural isomers which have different principal carbon chain or side chain or both. That means two compounds are given, they have same molecular formula, but their structures are different. Particularly, they have difference in length of carbon chain, otherwise length of a side chain, sometimes both length of carbon chain and a side chain. So if you want to use the word chain isomerism, chain isomers, they should have different principal carbon chain or a side chain. But most important condition is, in order to exhibit chain isomerism, the given compound should have minimum of 4 carbon atoms. But after understanding the definition, after solving some questions, by default you will understand these conditions and all, need not to memorize. So let us understand the definition of chain isomerism by taking example butane. So butane, basically it is alkane, so that is a C4H10. Here, for the sake of convenience, I am writing only the carbons, and I'm not going to satisfy the tetravalence of carbon because that will kill the time. Obviously, that is understood. For example, if you take butane, 1, 2, 3, 4 carbon atoms, and again I'm writing one more butane like this. But please understand, here we have 3 hydrogens, 2 hydrogens, 2 hydrogens, 3 hydrogens. Here 3 hydrogens, 3 hydrogens, 3 hydrogens, and this is having 1 hydrogen. To understand chain isomerism in a better way, let us write only the carbons, and of course every carbon shows tetravalence, that is you already know. If you see, in case of the first butane, length of carbon chain, it has 4 carbon atoms. And if you take the second butane, it has only 3 carbon atoms. But no doubt, they have same number of carbons, same degree of unsaturation. By default, number of hydrogens will be same. Unnecessarily don't count the number of hydrogens. First you check the number of carbons. Number of carbons. Here also number of carbons is same. Degree of unsaturation is 0. Here also degree of unsaturation is 0. And there is no heteroatom like a halogen, oxygen, nitrogen. In that situation, instead of counting number of hydrogens, simply you just take it for granted if number of carbons and degree of unsaturation is same, 100% number of hydrogens will be same, because however heteroatoms are absent. But this is true only when heteroatoms, other elements are absent. When you are dealing with hydrocarbon, instead of wasting time on counting number of hydrogens, you just check number of carbons and degree of unsaturation. And obviously this is having 10 hydrogens, this is also having 10 hydrogens. But if you see the connectivity, here the connectivity you can see all are carbons present in a normal chain, but here only 3 carbon atoms are present in normal chain, one carbon is present as a branch. So this is carbon chain with 4 carbons, this is a carbon chain with 3 carbons. Therefore these two are said to be structural isomers, more particularly chain isomers. Let us take another example, that is pentane. The molecular formula is C5H12. Degree of unsaturation will be 0. Already told you I am writing only carbon atoms. So here totally we have 5 carbons. 5 carbon chain you write first. Next 4 carbons. Here I am keeping 1 carbon like this. One more pentane I am writing. So here 2 carbons. But later in the next video, while solving the questions on structural isomers, how to write the structural isomers, there I will discuss. But we are just understanding the definition. You can see this compound is having all 5 carbon atoms in the principal carbon chain, but the second pentane is having only 4 carbons in the principal carbon chain, but whereas the third one, if you see, only 3 carbons. This is 5 carbon chain, 4 carbon chain, 3 carbon chain, but they have same molecular formula. All three are having same molecular formula, but they have different principal carbon chains. Therefore they are said to be chain isomers. So let us take one more example, that is a hexane. Hydrocarbon, degree of unsaturation is 0. So 1, 2, 3, 4, 5, 6 carbon, 6 carbons in chain. Now I am taking 5 carbons. Here one branch I am taking. Next let me take 4 carbons. Here one branch, here one branch. So this is the first one. It is a 6 carbon chain. It is a 5 carbon chain. It is a 4 carbon chain. They have same molecular formula, but length of carbon chain is different. Therefore, these are said to be chain isomers. Even you can observe one more example here. Of course, here OH and OH functional group is the same. So 1, 2, 3, 4 carbon chain, but this is a 3 carbon chain. Length of carbon chain is different. This is having 4 carbons, and this is having only 3 carbons in the principal carbon chain. Next, carboxylic acid. This is also carboxylic acid, but the first one is having 4 carbons in the principal carbon chain, but this is only 3 carbon chain. One carbon is present as a substituent. And even if you take the first one, it is having 4 carbons in the principal carbon chain, but here it is having only 3 carbons. So this is about the definition of chain isomerism. The third type of structural isomerism is functional group isomerism. First, let us understand the definition properly, because while writing structural isomers or while identifying the relation between given structural isomers, definitions are at most important. So the structural isomers which differ in type of functional group. So one isomer has one type of functional group, another isomer has a different functional group. If you find difference in functional group, definitely they are said to be functional group isomers, and this phenomena is a functional group isomerism. So whenever you are identifying that the given compounds have different functional groups, need not to check length of carbon chain, need not to check the position of the functional group. If functional group is different irrespective of all parameters, the given isomers are definitely said to be functional group isomers. Definitions are very much important. If you take some examples here, alkenes and cycloalkanes. For example, here I am taking C4H8, degree of unsaturation is 1. When degree of unsaturation is 1, here it is hydrocarbon. I am writing one structure, that is a butene, open chain compound, and with the same molecular formula I am writing a different structure. So here in case of the first one, the functional group is the CC double bond, and here the functional group, in fact there is no functional group, we have to say, that is a CC single bond. This is alkene and this is a cycloalkane. Not only functional group isomers, they are also said to be ring chain isomers. And the second example, alkynes, alkadienes, cycloalkenes and bicyclic compounds. Alkynes, for example, here I am taking C4H6, degree of unsaturation is 2. We can write a triple bond, it becomes a alkyne. We can write two double bonds, it becomes alkadiene. We can write a cycloalkene, degree of unsaturation is 2. I'm just satisfying the degree of unsaturation and number of carbons. So ring is one ring and one pi bond, degree of unsaturation is 2. Even we can write a bicyclic compound like this, bicyclic compound. So here functional group is a triple bond, functional group is a double bond. Of course this one and this one also functional group isomers. Here we have double bond, here also we have double bond, but different functional groups we can write. That's what I'm discussing here. Next one, alcohols and ethers. In case of alcohols and ethers, they have general formula CnH2n plus 2O. If you can recollect, while finding degree of unsaturation, oxygen does not affect the degree of unsaturation. While converting this oxygen compound into corresponding hydrocarbon, you have to remove oxygen without disturbing number of hydrogens. If you can recollect that point already we discussed in degree of unsaturation video. CnH2n plus 2, so degree of unsaturation is 0. Here I am taking C4H10O, and here the structure I am writing is like this, and another structure I am writing will be like this. So alcohols and ethers are functional group isomers, but you need to check whether they have same molecular formula or not. One is having 4 carbons, another one is having 3 carbons. In that situation they are not at all isomers. They should have same molecular formula. Next one, aldehydes and ketones. In case of aldehyde functional group, ketone functional group, degree of unsaturation is 1. Hence the molecular formula, the general formula will be CnH2nO. CnH2nO. When you convert this into corresponding hydrocarbon, simply you have to remove oxygen. As a result, it becomes CnH2n. CnH2n, obviously degree of unsaturation is 1. Here I am taking C4H8O, and here one functional group. In one molecule, the functional group I am writing is aldehyde. In another isomer, the functional group I am writing is ketone. You can see they have same molecular formula but different structures. And particularly in case of structure, what is the difference you are finding? Here the functional group is aldehyde, here the functional group is ketone. So whenever the two compounds or two isomers are functional group isomers, don't check the length of carbon chain, don't check the position of the functional group. Once the functional group is different, simply they are said to be functional group isomers. And next one, carboxylic acids, esters, hydroxycarbonyl compounds. Carboxylic acid, you know, COOH functional group. COOH means there are two oxygens and the degree of unsaturation is 1. So the general formula of the compound is CnH2nO2. CnH2nO2. Let me take one example, that is C4H8O2, and one structure I am writing, that is carboxylic acid. You can see this is carboxylic acid, and another structure I am writing, so that is ester. So this is 1 2 3, so 4 carbons. Even we can write a hydroxycarbonyl compound. Hydroxycarbonyl compound we can write. So this is OH group, and here this is aldehyde. Already told you, whenever you are checking degree of unsaturation, whenever you are writing different possibilities, first you check the degree of unsaturation. Here you see 4 carbons, 2 oxygens, degree of unsaturation is 1. 4 carbons, 2 oxygens, degree of unsaturation is 1. Even this 4 carbons, 2 oxygens, degree of unsaturation is 1. In that situation, don't waste time by counting number of hydrogens. Once the degree of unsaturation is the same, 100% they will have same number of hydrogens. So carboxylic acids and esters, hydroxycarbonyl compounds, these are functional group isomers. And the next one, primary amines, secondary amines and tertiary amines, always they are said to be functional group isomers. So here let me take for example amine with 4 carbon atoms I am taking. So here this is primary amine, 1 degree amine, 4 carbon atoms, you check 1 2 3 and 4. Next secondary amine I am writing, number of carbon atoms is same, number of nitrogens is same, degree of unsaturation is same. Unnecessarily don't count the number of hydrogens. Next I am writing a tertiary amine. So here primary amines, secondary amines and tertiary amines, which are having the same molecular formula, are said to be functional group isomers. 1 degree amines, 2 degree amines and 3 degree amines are functional group isomers. Next one, cyanide and isocyanide. Cyanide and isocyanide, these are also functional group isomers. You can see totally 3 carbon atoms are present. Here also 3 carbon atoms and 1 nitrogen, but here the functional group is cyanide functional group, here the functional group is isocyanide functional group. Next one, nitroalkanes and alkyl nitrites. Nitroalkanes, for example I am taking nitroalkane with 3 carbon chain, and alkyl nitrite, this is ONO. Already told you, once a functional group is different, simply they are said to be functional group isomers. Don't check the position of the functional group. Once a functional group is different, simply they are said to be functional group isomers. Next type of functional group isomers are 1 degree amides, 2 degree amides and 3 degree amides. Every time we are saying isomers, so they must have same molecular formula. Here I am taking amide with 4 carbon atoms, and the structure I am writing is like this. In this, if you see the classification, this is 1 degree amide because here we have NH2 group. This is primary amide. Now I am taking amide with the 4 carbon atoms, but here if you see totally the number of carbon atoms same, 1 2 3 4, but here this NH nitrogen is attached to an alkyl group, therefore it is a secondary amide. And one more category let me write. So here that is a C double bond O N CH3 CH3 CH3, here I am writing hydrogen. So every structure what I have written here, all of them are having 4 carbon atoms and amide functional group. But here this is 1 degree amide, this is 2 degree amide and this is 3 degree amide. Primary, secondary and tertiary amides are functional group isomers. So these are the different types of examples for functional group isomers. And the most important point is, once functional group is different, don't check the remaining parameters like length of carbon chain and position. Once functional group is different, they are said to be functional group isomers. And the next category, metamerism. metamers, metamerism, metamers. First, let us understand the definition. Yes, these are basically structural isomers which have different alkyl chains on either side of a functional group. They should have same functional group, point number one, but the difference must be alkyl chains on either side of the functional group. Either side of the functional group, alkyl chains must be different, then they are said to be metamers, and this phenomena is metamerism. So, in order to understand the definition of this metamerism, let me take an example here. I am taking oxygen is the functional group, ether functional group, and here one side I am taking alkyl chain ethyl group. Here also I am taking alkyl chain, that is ethyl group. So, in this structure, functional group is attached to two ethyl groups. I am writing another structure, but one side it is having methyl group, other side it is having propyl group. See, this is one structure, this is another structure, and this is a functional group. On either side of the functional group, alkyl chains are different. You see, this side it has ethyl group, but here it has a propyl group. Here this side it has ethyl group, but the second one it is having methyl group. So alkyl chains attached to functional group are different, therefore they are said to be metamers. So this one and this one are said to be metamers. So in order to exhibit metamerism, the functional group should be attached to two alkyl chains. It means it must be a bivalent functional group. So, like what are the examples? Just now I gave ethers as one of the examples. You can see ketones. Ketones can exhibit a metamerism. Esters can exhibit a metamerism. Esters, because this side it has a carbon chain, alkyl chain. This side also it has alkyl chain. Esters can exhibit. 2-degree amines can exhibit. 3-degree amines can exhibit. Secondary amides can exhibit. Tertiary amides can exhibit. So these are some examples. But for example, if you take aldehyde cannot exhibit a metamerism because it is having hydrogen one side. So the functional group should have two alkyl groups. Functional group either side there must be alkyl groups. So these are some examples. Now let us take a one by one. So here the first one, ethers. Ethers can exhibit metamerism, already we discussed. So here this is diethyl ether, and one side I am taking methyl group, other side I am taking propyl group. Secondary amines can exhibit metamerism. Both the sides I am taking ethyl groups, but they should not be functional group isomers. You should not write tertiary amine. Once functional group is different, they are said to be functional group isomers. Tertiary amines, 3-degree amines, like this, all ethyl groups, for example, tertiary amines. Now methyl group, propyl group, ethyl group. If you count the number of carbons here, each ethyl contains 2, 3 into 2, that is 6. 1, 2, 3, 4, 5, 6. So alkyl groups attached to a functional group are different, therefore they are metamers. Esters can exhibit, yes, esters can exhibit metamerism. Here if you see, methyl group is attached to oxygen, but here we have ethyl group. So methyl group and ethyl group, you can see ethyl group is attached to carbon. Here methyl group is attached to carbon. So these are said to be metamers. Thioethers, like ethers, thioethers also exhibit metamerism. Alkyl groups attached to functional group are different. Sulfonic esters. Normal esters are COOR, but here it is SO3R. So that is CO2R, this is SO3R. So here like this, here I am taking methyl group. Here I am taking ethyl group. Let me write a different structure by changing alkyl groups. Now oxygen is having ethyl group, sulfur is having methyl group, so they are metamers. Acid anhydrides. Acid anhydride is the functional group. Definitely it is having two alkyl groups. For example, here I am taking propyl group, here I am taking ethyl group. You can change the structure. So here O, C double bond O, this side I am taking methyl group, this side I am taking butyl group, like this. Secondary amides also exhibit metamerism, like this. This side I am taking R, this side I am taking R prime. Now R prime, C double bond O, NHR. R prime nitrogen is having, R nitrogen is having. Similarly, tertiary amides also exhibit a metamerism. Functional group should have two alkyl groups. Functional group should be attached to two alkyl groups. So these are the examples of metamers. Last type of structural isomerism, ring chain isomerism, ring chain isomers. Understanding the definition is important. So structural isomers in which one has a closed chain and another one has a open chain. So carbon framework is different. In one isomer we have a closed chain, that is ring structure. In another isomer we have open chain. Such type of isomers are ring chain isomers. Already we discussed, so that is C4H8. In case of C4H8, so here this is, for example, open chain compound, and another one I am taking, that is a closed chain compound. So these two are also known as ring chain isomers. In one isomer it should be closed chain, in another isomer it should be open chain. So these are the definitions of various structural isomers. Now let me give some hints on structural isomerism. The first one, if a functional group is different, then they are functional group isomers irrespective of a length of carbon chain and position of a functional group. First you check the molecular formula. If you find difference in functional group, straight away you say they are functional group isomers. Don't consider length of carbon chain, don't consider the position of a substituent. Next one, positional isomers should have same length of carbon chain. If you are saying they are positional isomers, length of carbon chain must be same. If length of carbon chain is different, they are definitely chain isomers. If a functional group is different, they are definitely functional group isomers irrespective of length of carbon chain. But in case of positional isomerism and chain isomerism, generally the students confuse here. If you want to say the given isomers are positional isomers, the length of carbon chain must be same. If length of carbon chain is different, definitely they are said to be chain isomers. But functional group must be same. Length of carbon chain is different, then they are obviously said to be chain isomers, but don't use the word positional isomers or positional isomerism. And here if you see the table, here serial number, difference, type of isomers. If length of carbon chain is different, then they are chain isomers. If a position of a substituent or position of a functional group that is different, then they are said to be positional isomers. If a type of a functional group is different, then they are said to be functional group isomers. If alkyl groups attached to functional group are different on either side, then they are said to be metamers. If there is a difference in carbon skeleton, then they are said to be ring chain isomers. So this is about structural isomerism, complete concept of structural isomerism. In the next video, we will discuss some questions how to write structural isomers. Thank you very much.